In this lesson, we'll take a look at how our understanding of the hippocampus can guide us in the use of study techniques in school. So we'll look at the implications for school in these areas here. First, let's think about attention. In previous lessons, we learned that one form of forgetting we called storage failure, where the learning event just did not produce a strong memory trace. So we'll call that storage failure. Now, one common cause of that is poor attention. If we go back to this diagram here, we have a couple patches of cortex, auditory cortex, visual cortex. So this area is processing what we're hearing and what we're seeing of some lesson we're engaged in. And of course, those areas are sending information down to the hippocampus so we can make a hippocampal memory trace that links the cortical memory traces. Well, attention increases the sensitivity of neurons in the cortex. So cortical neurons respond more strongly to whatever information they are receiving. And likewise, the hippocampal neurons respond more strongly because they're receiving stronger signals from cortical neurons. So the overall effect of this is that attention makes the cortical and hippocampal memory traces as strong as possible. If we're not paying attention, we're going to have very weak cortical memory traces and weak hippocampal memory traces. And we've previously learned that we need the hippocampus, the hippocampal memory traces, to retrieve information soon after learning, because those weak cortical memory traces are unable to be found and activated by the cortical retrieval systems. So if we have a weak hippocampal memory trace, we're going to have difficulty retrieving the information soon after learning. And in addition, then when we go to sleep, we'll have ineffective consolidation during sleep because we'll have weak hippocampal memory traces. And you'll recall during sleep, we fire up the hippocampal memory traces to strengthen the cortical ones. But if the hippocampal memory traces are weak, that consolidation process will not be as effective as it could otherwise be. Now, attention is key to learning. There are several things that can interfere with learning that are related to attention. So distractions, so we're shifting our attention, and that can impact learning negatively. Fatigue, again, that can have its effect through attention, through poor attention, and likewise stress. So these things are not good for learning, and the reason they have a negative effects on learning is in part that they're affecting attention. Using our brain diagram here, attention is amplifying neural activity in the sensory areas that process the learning event. So there are frontal cortex attention systems, and they really send physical signals along axons, right? Electrical signals back to the areas of the brain that are processing whatever we're attending to. Now, we might be just focusing on what we're looking at and not paying attention to sounds in our environment. Well, in that case, the attention signals would only be amplifying the visual cortex and not so much the auditory cortex, or vice versa. But the idea is that attention, the effect of attention, is to amplify neural activity in the areas of the brain that are processing the information from the world. Now notice the paper with the pen applying ink. So this is our metaphor that when we're making memory traces, it's like applying ink to paper. And so attention is going to make these memory traces stronger in that brain area. If we're not paying attention, then notice the amount of ink in these memory traces, both in the cortex and in the hippocampus. So with attention, poor attention. Good attention, poor attention. So attention is the key to learning, where if we want to learn stuff, we've got to be paying close attention. What about deep processing? Well, we've heard that psychologists recommend using deep processing techniques in our study practices. These are the kinds of techniques that seem to produce memory advantages compared to other techniques. And we've done a few experiments in class with word lists, and we found that evaluating a word, pleasant or unpleasant, is a deeper level processing task compared to counting syllables. It produced a memory advantage. Likewise, drawing was a deeper processing task than just writing a word repeatedly. And the idea here is that the deep processing tasks are using more brain areas or activating brain areas more intensely. And as a consequence, the brain can store information better and retrieve it better later on. To bring the hippocampus into the story, deep processing tasks, again, sort of the widespread brain activity here, the little icons would be different parts of the brain being activated. We're going to get stronger memory traces as a result of a deep processing task. With a shallow processing task, not as much brain activity, we're going to have weaker memory traces. And again, the importance of this is that with stronger hippocampal memory traces, there will be better retrieval soon after learning. Over here on the left, you'll recall from a previous lesson that we need the hippocampal traces to retrieve recently learned information precisely because the cortical memory traces are weak. If we don't have a hippocampus like HM, the cortex just can't find and activate these weak memory traces. We need our hippocampus to access recently learned information. But then we go to sleep. And during sleep, we do the consolidation process. We activate hippocampal memory traces and we strengthen the cortical memory traces. Well, if the hippocampal memory trace is weak, then this consolidation process will not be as effective as if we had strong hippocampal memory traces. Now let's see how the hippocampus sheds light on this recommendation to use repeated short study sessions. All right, so in a previous lesson, we did learn that cortical neurons and hippocampal neurons seem to have different levels of plasticity. Cortical neurons had lower plasticity, hippocampal neurons had higher plasticity. And this has an important implication for our studies. We've got to repeat our study sessions. Why is that? Because the cortical neurons, that's the long-term memory system, with low plasticity, it means that we have to activate them multiple times. We have to study multiple times to give the brain an opportunity to grow these synapses really nicely and strong, so we have strong cortical memory traces. We've got to repeat our study sessions. Using our brain diagram, notice we have multiple files in different parts of the cortex here, with the file on the right having the most ink, indicating the strongest memory trace. But that was only achieved with repetition. So when we study on multiple occasions, then we can trigger multiple rounds of consolidation during sleep, and we can build stronger and stronger memory traces in the cortex. Notice down here in the hippocampus, we've got 3 separate hippocampal memory traces. Now they're all strong down here. Every time we study, right, spaced out in time, we're going to make strong hippocampal memory traces. But when we go to sleep and do consolidation, we're strengthening the very same cortical memory traces. See, because these are the memory traces for the same information we're studying on multiple occasions. But it's just that on each study session, we might have different hippocampal memory traces that are going to be strengthening the same cortical memory traces. Using our analogy again, every time we go to sleep and do a consolidation, it's like the hippocampus is printing or applying more ink to those cortical memory traces, strengthening them to such a degree that we won't even need the hippocampus any longer to retrieve that information. Now, if you're in a pinch and you just have to study one day before an assessment, you want to space out your study sessions. By creating delays between study sessions, then you increase the chances that new hippocampal memory traces can be made and used for consolidation during sleep. So by spacing out study sessions, then we're helping the brain kind of create new files here, each of which then can be used during consolidation to strengthen the very same cortical memory traces. But ideally, you want to have sleep in between study sessions, so you get the full effects of memory consolidation during sleep. Of course, cramming then, when you study once before the assessment, it's going to deprive your brain of the opportunity to make stronger memory traces. So in the cramming brain, we don't get to have strong memory traces as a result of multiple study sessions. We are left with weak cortical memory traces because we only studied once. Maybe we went to sleep, but still, we're going to have weaker memory traces than we otherwise could have if we studied multiple times. At the level of synapses, we're going to have relatively weak synapses, and that's why the memory traces are weak. Now, you might do okay on the quiz, but you are very likely to forget the information quickly. Now, what about the recommendation for short study sessions? Well, now we have to shift our focus to the hippocampus. Recall we said the hippocampus has high plasticity, so the neurons there can grow very strong synapses with one learning event, one study session. And let's zoom in on some hippocampal neurons here. So here we are awake and we're learning in a classroom or watching a video lesson or reading a text or whatever. Well, that learning event is going to produce rapid changes among some hippocampal neurons. So we're going to grow strong synapses representing this new learning. However, there are limits to plasticity. And the thing is, if this growth happens quickly in the hippocampal neurons because of their high plasticity, then with long study sessions, no further gains can be made in synapse strength. And remember, right, when we're learning is the result of growing synapses. Well, if we've already maxed out our hippocampal synapses, we can't learn anything more. So the recommendation here is to use short study sessions. Hippocampal memory traces get strong early in the study session. Prolonged study of the same information loses effectiveness. And now let's take a break. We'll take an intermission and we'll return with an examination of how the hippocampus sheds light on the reasons we should get good sleep if we want to be good learners. Okay, let's return to the implications for school and let's take a look at sleep from the point of view of the hippocampus. Well, we've already learned about this, that two really important things happen during sleep, and they involve the hippocampus. On the left, in the consolidation phase of sleep, we're going to fire up the hippocampal memory traces from the day's learning so as to strengthen the cortical memory traces. But then, to prepare the hippocampus for new learning, the brain will weaken those hippocampal memory traces. So we're going to refresh the hippocampus so the hippocampus is ready to make new memories. But we want to keep our memories in the cortex. That's the long-term system. In a previous lesson, we learned one of the reasons why, or several reasons why the brain does this consolidation process. There are just more neurons in the cortex. With more neurons, you have more synapses. You can store more information. So you can build a lifetime of learning in the cerebral cortex. The hippocampus is a much smaller structure. Fewer neurons, fewer synapses. There's a limit to how much information the hippocampus can learn, but it's enough for a day's learning. And so this is a pretty cool system. It's a fast learning system. And then what we learn during the day, we use that information during sleep to build and strengthen the cortical memory traces. And then we weaken those memory traces to prepare for the next day's learning. So the system is sort of like we're integrating the day's learning into the long-term memory system. That's what consolidation is doing. All right, let's take a look at our final recommendation, retrieval practice. In previous lessons, we learned of two forms of forgetting: storage failure, where we don't make strong memory traces to begin with, and then a loss of access, where we do make strong memory traces, but then our brain loses the ability to find those memory traces. Now, why would that happen? A failure to use retrieval practice. Take a look at the diagram on the left here. Here we have a situation where the person has studied repeatedly. Let's say they've got strong cortical memory traces and they've been retrieving that information on a regular basis, so they have strong retrieval pathways. This is the cortical retrieval system. That's a recipe for success. This is the educated brain. This is a person who has quick, reliable access to their knowledge. But if now they go for an extended period of time where they don't retrieve this information, what you get is something on the right here. We can still have strong cortical memory traces for that information, that knowledge, but it seems as though the brain now has trouble finding those memory traces. And we can kind of think of this as the retrieval pathways have weakened. Now, scientists think that, well, there's a couple ways we can think about this. Either the pathways are attempting to activate the wrong patches of cortex that don't even have the proper memory trace, or maybe the retrieval system is finding the memory trace, but just the nature or the amount of activity is insufficient to successfully retrieve the information. So the cortical memory traces are present and strong, but the memory search failed to find or activate the correct memory traces. Now, what's the evidence for this story here? Well, one piece of evidence is the following, that when we relearn the information, it leads to rapid recovery of strong retrieval, faster than what occurred during original learning. So it's like sort of having, your old phone number or your old address. At one time you knew it well. Well, it's stored strongly in your cortex, but if you move and you haven't been at that old place for 10 years, you might have forgotten the phone number or the address or whatever. But if somebody comes along and tells you that, then you quickly regain access to that information. It's as though the relearning strengthens again the retrieval pathways so that now the brain can find that information successfully like you used to do years ago. In addition, we expect, theoretically, that the memory traces in the cortex are going to have a slow rate of synapse decay, right? And that makes sense for the long-term memory system. I mean, if the synapses in the cortex just kind of weaken over time, then we don't really have a long-term memory system. And we know that we do. We can learn things and remember things for a lifetime. So by theory then is that we can make strong cortical memory traces, but somehow with disuse, the brain loses access to that information. If we think about the cortical neurons in this diagram here, we have slow learning, right? So we need multiple study sessions to build strong synapses, but we have slow decay, and that makes good sense for a long-term memory system. Now, from an evolutionary point of view, life events that happen repeatedly are likely to be important for survival, so worth storing. So the brain seems to store information that happens repeatedly. So repeated events in our lives are going to be well represented as memory traces in our brains. Now, in school, when teachers and parents recommend that we repeatedly study, well, we're sort of trying to trick the brain into assigning importance to the information. So repeated information is going to be stored well in the brain because these cortical neurons need repeated activations to grow strong synapses. But even if the memory trace is strong, we must occasionally retrieve such memories to maintain quick and reliable access to that information. And that's what retrieval practice does. Retrieval practice strengthens the retrieval pathways and so prevents an important form of forgetting. So with retrieval practice, we keep on giving the brain practice at finding our strongly stored information. And so we won't ever have this form of forgetting because we'll keep our retrieval pathways nice and strong. But importantly, it is true that retrieval practice also strengthens cortical memory traces. Each time we retrieve a memory or fail and restudy, it triggers another round of consolidation during sleep. Just think about the act of retrieving again on this brain. So let's say our cortical retrieval systems successfully activated some cortical memory traces, and now we're having a retrieved memory experience. But remember, we have the conscious experience of it because of the sharing of information from these cortical regions, but those same cortical regions also send information down into the hippocampus. So a retrieved memory that is in working memory can be restored in long-term memory because those cortical areas that stored the memory also communicate with the hippocampus when retrieving the memory. And then at night, we use that hippocampal memory trace to make the cortical memory traces even stronger. So every time we retrieve a memory, we can make that memory stronger. So there we have it. Understanding our hippocampus can guide us to effective study strategies. We want to pay attention when learning. We want to repeat short study sessions with deep processing techniques. We want to space out study sessions with sleep in between and use lots of retrieval practice.